Hi, today I want to work with my complex linear algebra library. I want to work on the network analysis using linear system. This is the first network analysis. This is the first network analysis. Okay. I have drawn this network here. Alors, the rate of flow into any node, the rate of flow into any node is equal to the rate of flow out of that node, is equal to the rate of flow out of this node. For example, you have here the node A, the input are x1 and x2, and the output is 50. For the node B, the input are 40, and the output are x2 and x3, for the node B. For the node C, the input are x3 and x4, and the output are 20. For the node D, the input are 30, and the output are x1 and x4, x1 and x4, okay. I have right is 4 equal 10. I have right here is 4 equal 10. Now I want to analyze this network. I rewrite this equation in this way. I have given the value 10 to x4, 10, x4, 10. Alors, let's fix the system. x1, x2. I have put the number on the right and the xn on the left. Now I have rewrite the system in this way. Why? I have put in the first column x1, the x1. I have put in the second column the x2. I have put in the third column the x3. I have put in the 1, 2, 3, 4, 5 column. I have put the numerical value, and I have added a column of 0. Why? Because I have 1, 2, 3, 4 line and 1, 2, 3 column. with the row 0, I have 4 columns and 4 lines. This is the code in C language. We work with complex value, so you have here the imaginary part. Now I want to copy the C language code for this work. You can see here the linear system. I have right preset here. Yeah, right here. This is the system. Okay. And now I can, here I use Gauss-Jordan. Okay, I use Gauss-Jordan. I print A, I print B, I print AB, the system. Even if I work with complex value, I print only real part because the imaginary part are 0. The imaginary part are 0. Now I can use Octave to resolve this system. This is a result given by Octave, and this is my result. Okay, you have the same value. You can see you have here the column of 0, and you can see I have here a line of 0. Why? Because I have only 3 unknown. I have only 3 unknown. Also, I have only 3 values. x1 is 20, x2 is 30, and x3 is 10. I only use the function Gauss-Jordan. You can use, instead Gauss-Jordan, you can use the QR factorization. You have here R. You can download. You can eventually, if you want, you can verify the QR factorization with Octave. All right. You have here the factorization with Octave, and you have here the factorization with my function. Now you take the conjugate transpose of Q, and the inverse of R. You know R is a triangular matrix, so it is more easy to take the inverse. It is why you can use a QR factorization to resolve a system. And now I have the result. This is the result. To obtain the result, you must multiply B by conjugate transpose of Q and inverse of R. It is the same result that the first example. You have here the result in octave 20, 30 and 10. 20, 30 and 10. You can use also the X value decomposition. The code in C language for the QR factorization, you call the function QR, you obtain Q and R, you print here QR, you print with, you use AR here because you want only print the real value. You take here the conjugate transpose of Q. You can take here the inverse of R, and now you can multiply inverse of R by Q, conjugate transpose of Q, and then you multiply this value by B, and you have the result. Now I want to work with the X value decomposition. I have R, B, I compute U, I compute V, I multiply the conjugate transpose of U by A and then by V, and this gives a diagonal matrix. I take the inverse of this diagonal matrix. Why? Because it is easy. Then I can compute the pseudo-inverse of A. In this way, I multiply by the left V and by the right the conjugate transpose of U, and this gives the pseudo-inverse. Now, if I multiply if I multiply A by pseudo-inverse, this gives the identity matrix, and if I multiply the pseudo-inverse by B, this gives a solution 20, 30, 10. 20, 30, 10. You print here A, you print here B, you compute here U, you compute here V, you compute the conjugate transpose of U, the conjugate transpose of V, and now if you multiply, now if you multiply the transpose of U, conjugate transpose of U multiplied by A by V, you have a diagonal matrix. This is here, you have the diagonal matrix. Then you can compute the inverse of diagonal matrix. You only compute the inverse of the diagonal coefficient. This is this function. And then you can compute the pseudo-inverse. The pseudo-inverse. To compute the pseudo-inverse, you must multiply the inverse of diagonal matrix by V by the left, and by the right you must multiply this value by conjugate transpose of U, and this gives the pseudo-inverse. And then you multiply the pseudo-inverse by B, and you have the result. Why you must use the pseudo-inverse? Because A is not square. You have 1, 2, 3, 4, and 1, 2, 3 column. So this is not a square matrix, so you must use a pseudo-inverse to resolve this system. And you can see with this result you do not have a row and a column of 0. Alors, this is the first example. You can try on this page a second example and a third example. I am not able to make all the example because it is too difficult for me. Also, I only do this example, and you can try these two examples. Thank you.